So welcome to the 2-hour introduction to the Pandas Dataframe library. It looks like in actually about 20 minutes now, there is something starting over in Cartoon 2, Stumbling Blocks of a Python Newbie. And then at 11:30, there will be a slate of talks starting in a number of the other rooms. My plan, because this goes on the clock until 12:30, it's a 2-hour commitment you've made by sitting down. I know that some of you guys might get as much as you want out of your first hour here and want to head out. So my plan is at about 11:25 to break for 5 minutes so that if any of you want to hit the restroom or go hear the beginning of one of those other talks, you can do so. So I'll try to split this into roughly 2-hour segments. First hour, a short break, and then a second hour. This is going to be the sort of follow-up to a tutorial that I gave at PyCon this year up in Montreal for the first time. This last 2 years of PyCon. It had always been officially PyCon North America, but everyone always knew it was really PyCon US. And for the first time, a Canadian city put in such a compelling bid that we moved, and then my Canadian friends were ecstatic that finally we were the ones who had to get passports and discover 2 weeks before the conference, in some cases, that we could maybe not go until we expedited things. They were ecstatic that finally we were the ones having to be interrogated by border guards before we could attend PyCon. Anyway, a beautiful city, I discovered. No one told me until I moved to the Midwest a few years ago that Detroit was a border town. Because it's like, in the rest of the country, it's depicted as like this, the archetypal American city, and big iron, and cars are built there, and stuff like that. I never knew it's like right on the Canadian border. The map I had of the US as a small child, I actually went and looked it up on Amazon to confirm this. The little puzzle map I had of the US as a child just has water along the north and south borders. So I didn't even know you could cross over to Canada from Detroit, much less did I know that Canada is south of Detroit, which is still quite bizarre to me. But it was great. I was able to cross the border, park at the train station, and just sit with my laptop. They let you use your laptop before you get to 10,000 feet, and I was able, they don't scan all your bags before you get on the train. It's great. And I was actually able to just take land transportation all the way to Montreal. It was a really great conference. We're going to have it's back in the US, so it will be in Portland for the next 2 years. But my contribution this year was doing a 3-hour-long tutorial that this is based on. And so wanting to be able to do this here at a local conference like PyOhio, I faced the question, how do I get 3 hours of material and move it down to 2? One possibility would be to leave some stuff out. But I didn't want to leave anything out, and so I made the following observation, that of the 3 hours, about half of the time, maybe 2/3 of the time when I did this back in Montreal, was getting everyone's laptop set up, getting Pandas installed, getting everything working for everyone, and then in between each little lesson or unit I did, I would let everybody try out the ideas. And I decided that I could cut this tutorial to 2 hours, hopefully without any loss of material, if I simply left you out of the tutorial schedule. So what I did in Montreal was I would get a feature of Pandas, I would explain it and do a quick illustration, and then I would walk around the room helping Windows people with their installs. Just because they're always, that platform provides more problems for people typically. I would walk around and help people with their installs while everyone got to try out the idea that I had just illustrated. But because here we just don't have the time for me to help everyone get installed, This is a smaller conference. I don't have TAs that I've had time to train beforehand to get you guys set up. What I'm going to do is, instead of the kind of A-B pattern I did, showing something, letting you try it out, showing something else, letting you try it out, what we're going to do instead here is I'm just going to jump in and tackle the exercises. The reason in Montreal that I would show how to do something with pandas using one example and then have you guys tackle the exercises with another example is it would be pretty boring if you had just, 5 minutes apart seen me do something and then immediately tried to do exactly the same thing yourself. It would have been quite boring. But in this case, where I expect it will be until the end of the weekend, next week, or the following week, that you get a chance to sit down and try the exercises for yourself, I don't think it will feel like rote memorization, say Monday morning, next weekend. When you sit down to do these same exercises that you'll see me do right now, I don't, unless you have an extraordinary memory, you won't be saying, oh, this is boring, I just have to type in all of those angle brackets Brandon typed and exactly the same thing appears on the screen. You'll be seeing it a week later or a few days later, so I think you'll have forgotten exactly what I typed and you'll get to rediscover it over again. So in the interest of time, I'm simply going to do my own exercises in front of you to try to get you positioned so that when I hope you tackle them yourself, staring at that blank page in a week or two and start trying to rebuild these solutions for yourself, I hope having seen me go through them, make mistakes, solve each one, will put you guys in a good position to be able to use pandas yourself. Let me see, I will head over to when you install, and I will recommend, I'll make a series of notes that I'll add to these later. When you want to install pandas, I recommend that you install something called Anaconda. I'll provide a link to it. It is a distribution of Python that already has pandas, NumPy, SciPy. SciPy is a science kit for Python. The plotting libraries, everything already compiled and installed. They figured out that scientists, it was very difficult for them to use Python because to have all those standard plotting and math tools like pandas, you had to spend like a day installing all of this extra software on your system. So Continuum Analytics has something called Anaconda. It's what I'm using here. I just installed it. I clicked on or used its Python launcher. And as you'll see, all of the libraries we need to use here are up and running. When you bring it up, it shows you the current directory you're in with all of the different files. And this entire collection of exercises you can check out. It's up for public on GitHub. Simply look up my name and Pandas tutorial, and you can either check this out using the Git version control system if you know that, or I'll show you after the break. GitHub, if you ever look to the right-hand side, there's always a little button that says download as a zip file. And it gets the project you're looking at and just dumps it onto your hard drive as a zip file. So you don't even have to understand Git or version control to get the collection of files that someone's trying to share with you through GitHub. When you get those files on your hard drive and bring them up, you'll see a series of what are called IPython notebooks. IPython it stands for Interactive Python. It was originally a project where someone just wanted, when they brought up a terminal window and typed Python, and even normal Python has simple editing. You can go back to an earlier line and edit and then re-enter it. It has basic command line history. But they wanted something that would have tab completion. They wanted something that would have different colors. They wanted something where you could replay several earlier commands easily. So they invented something really fancy called IPython. It was just, I think, 3 or 4 years ago that somebody got the idea of hooking that up to the web. And they created a system let me give us a little more space here by you can turn off the header and the toolbar to buy yourself room. They made something where you can type some Python code, even several lines of Python code, for I in range 10, print I, and it will tell you that you're in Python 3 and you have to use parens. So first, let me, that font looks a little small for those of you in the very back of the room. I might have to use that font size some of the time because the amount of data we'll be looking at will require me to make things a little smaller, but for right now, I'll go up to a font size more like this. You can see that the arbitrary several lines of Python code I put here executed when I hit Shift-Enter. The Enter key doesn't do anything but move to the next line. You're not committing to running your Python code until you hit either Control-Enter, which just runs the current cell but leaves you where you are, and that's an easy way to just, you know, if you're iterating on a single piece of code and want to keep adjusting it, Control-Enter keeps you where you are. It is Shift-Enter that bumps you down, and you see now it is this cell down here that is selected. So Shift-Enter lets you move down a notebook, executing every cell. Control-Enter lets you sit on a single one. What got people excited about the IPython notebook were things like the fact that, first, in Python, there had previously been only two ways to interact. You could either give someone a .py script, which just runs top to bottom, boom, and exits. Person has very little control over the pace at which the script runs. Or you could say, hey, here's a list of 30 commands, paste them in one by one to a Python command line and see what they do. This lets you get a series of commands, and by putting them each in a separate cell, set them up where they all live in the same file, but where an interested party who downloads your notebook can execute them one by one. Also, when you save the notebook, the current output displayed there is saved with each cell. So if someone opens your notebook and just looks at it and doesn't try re-executing it, they can see exactly what that example code gave you, whether it gives the same thing on their platform or installation of Python or not. So this ability to have input and output, to have the record of everything you did in a particular interaction with Python saved away, shareable. You can put it on the web. There's a button that'll format it as a blog post where you can have, oh, this is fun. If you, so let's put in a cell that has output. You can tell it, hey, give me a cell that's not code, but that instead is text. And you can say, hello, PyOhio, we can type italics. And this is the standard format called Markdown. When you execute a text cell, it gets formatted on the screen. And since this was designed by scientists, you can say, and you can use that old mathematics language that mathematicians use called LaTeX. You can say, I can compute x plus y, or a big equation. That's how mathematicians talk. We can say the sum from, this is how mathematicians get to type, from I equals 0 to 100 of x to the I. And when you execute it, you get professional quality mathematics rendered right in your browser, right in your blog post, or in a PDF if you choose to export to PDF. There are even people that are advocating that in the future, scientists, that they dream of a day when all journals would only accept IPython notebooks as articles so that the referees could execute the notebook from top to bottom, essentially rerun the math and stats, and verify on their separate system, given a private copy of your science data, that they could come to exactly the same result. Because a big problem we have these days is economics papers where literally major results have to be retracted because they forgot to highlight everything in Excel when the grad student did the calculations. So the fact that this can mix paragraphs of text, then a code sample, then more paragraphs, makes it really compelling for sharing entire computations. I'm going to make the font size a little smaller. Other things you can do is if you want to run a shell command, you can, well, first you can just put an exclamation point and type something like ls and look at all the files in the directory, ask what directory you're in. If you want to save the output of a command, you can say, I believe it's equals exclamation point, and you now get a Python list that has every line of output from the command that you just ran. So this makes it really, really easy to let the shell do things like finding files that it makes really quick, and then lets you hop over to Python for doing things like interpreting or loading up their contents. And then one of the things that made scientists most excited about this, data scientists, is the fact that we can say, let's see, pylab in line. We can do things like ask for, and I often don't remember how this, let me think, a range. Okay, let's say I want all of the numbers from -12 to 12, and let's ask for a step size of 1. So it'll go -12, -11, -10, all the way up to 11. Right, move out, okay. With a smaller font size, this doesn't wrap oddly like that. It's attempting to display it prettily here. This is what's called a NumPy array. NumPy arrays are one of the technologies behind Pandas. Normally in the Python language, if you need a list of a dozen numbers, it allocates a dozen objects in memory. And if you study how memory management works, you'll know that that's horrible. If you have a million numbers, you don't want to have to build a million objects in memory because they cost at least like 48 bytes a piece and burn a lot of memory. A NumPy array like this one that I asked the arange constructor to build for me only takes as much as the same array in C or Fortran. It has gotten all, how many numbers is this, about 2 dozen? Yeah, it's gotten all 24 of these numbers, and it has laid them out in raw memory using the same format that the C language, Fortran, using the byte layout native to the math coprocessor in your computer. So they are taking as little memory as they possibly can, and you can do math with them. I can say x plus 1 or x times 1,000, and a highly optimized, tight loop written in either C or Fortran, whichever is fastest for this problem, goes to work getting all 24 numbers and multiplying them by 1,000, adding 1, subtracting 1, whatever operation you do, it hands it over to the math coprocessor into highly optimized code to get it done. And that's how scientists can use Python. If you had to have a separate floating point object for all 2 million numbers in a science data set, it would take a lot of time to get them all multiplied by some factor. But this array is a single Python object that when Python says, hey, array, could you multiply yourself times 1,000? It allocates room for 1,000 new numbers in memory and extremely efficiently gets all of that work done. All a scientist has to say is x times 1,000. And for the cost of a single Python operation, they can have millions of numbers multiplied. And again, this is something we'll see, a technology that's very much behind how Pandas works. Finally, this lets you do things. The plot operator expects to be given one vector or array with a bunch of x locations, and then a second vector of exactly the same length that has the corresponding y locations. So I could do something like this. Sine of y is just like, sine of x is just going to get x and do something to it, like that, and just give us a bunch of floating point numbers. And what plot is going to do is it is going to assume, it's going to get all those x's and all those y's and plot them next to each other. We don't get very smooth curves with a step size of 1, So let's move it to a step size of 1/10. We now have a length of 240 different items. And if I come and now re-execute this cell, we now get a fairly smooth sine wave. These tools delight people who work with numbers because in a lot of languages, taking the sine of 240 numbers is often more code than this. But, and I recommend, if this interests you, watching Jake Vanderplas's talk from PyCon Montreal on NumPy. I think he called it looping without looping, because you just write sine of x, and automatically hundreds or thousands of sine operations take place, and it lets you write, fairly concise, what looks like the Python code for operating on a single number x, and instead it's happening hundreds or thousands of times. One last lesson about the IPython notebook itself. I'll zoom out slightly so we can see a few of these cells together. Because the notebook is so freeform, I can jump back and edit and rerun a cell. Then I can jump forward and rerun another one. Note that the outputs here are not the outputs you would get if you just ran this notebook top to bottom. For example, the input number 18, when I entered x and hit Shift-Enter, was run back when x was that first A range I did with the step size of 1. -12, -11, -10. That is not what x looks like right now, right? Len of x is 240. X right now, if I rerun this cell, is 240 different numbers that are all 0.1 apart. And this is the danger I always find with IPython notebooks. I get so excited, I jump back and forth rerunning cells that two things can happen. One, I bring up the notebook later. I read it top to bottom, and it makes no sense. And I sit there, and I look at something like this, and I'm like, okay, it looks to me like x has 24 numbers. Why does it say 240 down there? It's a mystery. And only if I look at the indexes do I say, oh, wait a minute, that's input 25. That's input 30. That one was run later. I must have been jumping back and forth. The other thing I'll do is that I'll decide, I don't like the name x anymore. Let's call this m. But I'll forget to edit all of the others, and they'll work as long as this notebook is open because I set x to something. Watch this. I can take away completely the definition of x, and this still works because this is an open Python interpreter that I'm just typing lines of code into. If I come down here and try to plot, it works fine. Should I ever then close this notebook and reopen it, or simply restart? I've just restarted the copy of Python behind this notebook. I have a notebook that will print 7 numbers, that has this text, that runs 70, can grab these file names just fine. I'm just hitting Shift-Enter to run it from top to bottom. There's also something here, by the way, that will run an entire notebook afresh without you having to hit Shift-Enter, but we're going through this slowly. Shift-Enter, and all of a sudden, a cell that was working perfectly before is an error when I hand this notebook to my friend and they try running it afresh. So the fact that as long as your notebook is up and open, you're talking to a live copy of Python that remembers everything you've executed, whether you've left it in the notebook or deleted it by this point, can easily let you create notebooks where, oh, you move things around and forget that the next time you run it, it won't work in the order you've put it in. So one thing I always do before sharing a notebook is to restart the kernel and then just do a run all from top to bottom to make sure that there aren't any errors hidden in it from the fact that halfway through the notebook I came up with a more clever name for something and uncleverly forgot to go edit the earlier uses of that variable. Before getting into Pandas, I just wanted to give you a few basic rules of the road and an introduction to this IPython notebook because of the really, really incredible efficiency gains I and other people I know have experienced by being able to do, simply being able to save snippets of Python in order to share with myself later or someone else, and in a way that lets you see even graphical output, even math equations or notes you write to yourself right on the screen. So before I head into Pandas, any questions simply about the mechanics of the IPython notebook that I recommend that you use when you play with Pandas later, and that you will be using if you jump into the exercises, because as you'll see in a moment, I wrote them up as IPython notebooks. Yes? Anacondas, yes. Oh, yeah, so the question was, what is the relationship between Anaconda and the IPython notebook? Anaconda is a fresh distribution of Python that installs into a directory on your hard drive they call Anaconda. I like that. It prevented me from getting confused. And that copy of Python, if you use the default installer, already has all of these tools available. You can just open it up, say IPython notebook, and you'll have this tool up and running. If you wanted to do that with your system Python, you would have to go find each of the pieces, NumPy, SciPy, IPython notebook. You'd have to find all these different pieces and spend 30 minutes or more doing a series of installs to get the normal Python from the python.org website to have all of these different pieces. And because scientists don't like spending part of the day installing stuff, this Anaconda was invented so that you just get all of this for free with a fresh copy of Python that hopefully doesn't have the idiosyncrasies of your system Python. People on Macs especially are probably familiar with the fact that on the one hand, Macs ship Python. Yay, awesome decision, Apple. Unfortunately, it's one that they've kind of edited a bit so that some normal Python things don't work with it. Anaconda gets you up and running with a standard, normal, fresh copy of Python without a bunch of patches made to it by your vendor that has all of these tools installed already. Yes, it is even more important for Windows people than for Mac. Yes. And right after the break, when I have their website up, I'll show the list of Python packages that they offer, but IPython is one of those packages. All right, and the reason I spent, I guess, a quarter of our time together here on the notebook is one, you're not going to have any fun with Pandas if you were fundamentally confused about what on earth is this thing in your browser that I'm expecting you to interact with Pandas with. It's, in its way, it's a perfectly normal Python prompt, but that just lets you interact through the web seeing visualizations or images if they come back. And second, many people, like some people who took my Pandas tutorial said, I think I'll be able to use Pandas sometime. Oh, but the notebook I can use every day. And so I wanted to make sure I explained how on earth I got a copy of Python on my screen that's letting me interact through the browser. All right, I'm going to go back to the front page that came up when I ran the IPython notebook. Oh, we can see right here, because I didn't bother to give this little example a title, so it's just called Untitled, and you can see here, IPython is telling me that's up and running. What I'm going to do in order to accelerate, and as I explained before, get through as much of my Pandas material as possible, is I am going to skip the cutesy introduction that I did at PyCon to each of these topics. I'm going to jump right into my own exercises, and I am going to try solving them, explaining Pandas along the way. I wish there were a way I could have a config file in my home directory that would just always have the header and toolbar turned off when I brought up a notebook. because I spend an unreasonable number of seconds per year pulling down those two menus. And so if anyone from Continuum Analytics is watching this later, I guess I should create an issue in GitHub rather than talking to you on a video. So I guess I'll do that. What can? Oh, they have those now? Everyone, you can use, thank you, you can now use IPython. They didn't exist the last time I looked a year ago. You can now use profiles to do that. So I will try one during the break. All right. I am going to run matplotlib inline, which gives the graphing library permission to send images right back to the browser. Otherwise, it does do its default thing of saving them, I believe, to files for you. And I am going to import a single thing. And that's all we'll study today is the pandas library. Nobody wants to type the word pandas, ever. And so I'm using a form of the import statement, this is standard Python, that lets you give a more convenient name to a library that you're importing. I also find that the way pandas, the way the IPython notebook displays data is not very easy on my eyes. The only way to tell the titles apart from the data is their choice of bold versus non-bold text. So just for fun, I use a trick here that you can study later to, when I execute this cell, watch the data frame there. I just loaded up some CSS that to my eyes makes the data frames a little easier to read and makes it clearer to my eyes that the titles are a very different kind of thing than the data inside. All right, if I've gotten everything loaded up correctly here, I should be able to, okay, I just ran the cell successfully. This is something I don't spend a lot of time on, but one could do an hour-long tutorial just on from CSV on all of the issues that come up when you try to read in raw data. In this case, it's a CSV file, and because it's a fairly standard one, I didn't have to use a lot of options in order to get it read in. I had to use this option. I don't remember what it does, because that's not the topic of the tutorial. Oh, I know, it tells it that it should just use a simple, plain integer index for all of the rows in this data frame. And then I did something interesting. Instead of simply asking for the titles data frame to get displayed for us on my screen, which I could do like this, because one of the magic things about the IPython notebook is that you don't have to use a print statement. Thank goodness, because they need parentheses in Python 3. You don't have to use a print statement if the last line of code you write, this is also true of, I believe, the Python prompt, so they had the notebook work the same way. If the last line of code you write just is a bare expression, like X, then it will auto-display the value of that expression on the screen. You know, X minus 20, whatever expression is last gets auto-printed, which in an interactive environment like the Python prompt is really convenient rather than having to type print for every single thing you want to see. So what I have done here is I have created a new data frame, and if I simply said its name, you would think that my browser would crash. You would think that hundreds and thousands of movie titles would display on my screen. Thankfully, this probably happened to the Pandas guy the first time he tried loading any real data set up. So Pandas automatically, it prints, what, 20 or 30 lines, and then it's like, okay, seriously, I am not going to print all of the lines of this data frame unless you set an option requiring it to do so. So it does that famous thing that we do when we need to leave something out, ... And so you can see here it printed the top 30 lines of this data frame, and then just skipped about 215,000 lines, you know, like you do, and then has the last 30 lines. So you don't generally with Pandas have to be afraid of crashing your browser or just having to like kill and restart everything because you accidentally printed to the screen something with 215,000 lines. Anyone ever ran a program or ran some Python, like you didn't think about how much output was going to come out, and like you had to kill it and start it over? Pandas data frames are built for large data sets, so they have a lot of protections built in against you getting clobbered with too much data unless you ask for it. But in this case, I'm going to run, this is the first lesson in Python data frames, I'm going to run a little method called head. It gets a big data frame and returns to you a smaller data frame. Fully functional, you can run statistics on it and everything, but it returns to you a smaller data frame with the first few lines. Want to guess what the one is called that gives you the last few lines? Tail. Will let us see the last few. And both of those take parameters that can let you just peek at a few or a lot of lines of data. But very often, as soon as I've loaded some data up, and you will see me do this over and over and over, I tend to run head on it, just to remember the names of the columns, to get a feel for what's in the data set before I start trying to do operations on it. But this is what a data frame looks like. A data frame is two-dimensional. It has a number of columns which have values from top to bottom that correspond. For this tutorial, again, the one this whole series of Python notebooks were the basis of the tutorial at PyCon Montreal, and they're up online, and they are based on the Internet Movie Database. The repository comes with a script that will download the IMDb and build these CSV files for you. I believe that it skips movies with international characters in them because some Windows users, we just could not get them up and running correctly where that would work. And so you might find that there is an unfair bias against foreign language films here, just so that it doesn't crash Windows users. But it is a good subset of the IMDb, because I often find that one of the problems I had while learning was that I would read a tutorial on some science tool. So I'm unfamiliar with the science tool. I don't know what it's going to do. And they would run it on a data set that I had no intuitive knowledge about whatsoever. So they would do some operation, and an answer would come out, and I would have no idea whether the answer was right, whether I had written the correct thing. Whereas, if I type a line of code that I think is the question, in how many movies has George Clooney starred, and 10,000 movies come back, I know I've typed the wrong thing, because I have an intuitive sense for about how many movies George Clooney has been in, right? It should be in the dozens, not the thousands. And so I really carefully tried to focus this tutorial towards questions that you'll already have an intuitive sense for. You might not know exactly how many movies Judi Dench has been in, but you probably have a rough enough idea that you'll have, besides looking at my answer sheets and seeing if you get the right answer, you'll probably already bring to this data set a knowledge of what reasonable answers are. And so for this very first set of exercises, I am loading up a set of movie titles, which seems to have two columns. We'll see how to address them in a moment. One called title, one called year. And then down here, a second data frame, let me load it up, called cast.csv, which has many rows for each. I have no idea what order these movies are in. But and by the way, I did take all adult films, anything out, so I have no idea what this is. No, seriously, on the IMDb, if you look in my filtering code, you both have to remove that category of movie, but then I additionally marked normal movies, but that had that tag. They are two different things, it turns out, and apparently no one's marked that movie yet. I don't even know what a glockumentary is. But this is a data frame that has every single role in every single one of those 215,000 movies. And so what we're going to look at here is let's just because I'm going to probably be looking at the head and tail of these, see if the tail is any better. Oh, and of course, rerunning that cell is making it load the entire CSV back up. Notice, by the way, what the notebook is about to let me do. If this were I don't know what those movies are, so I feel better about them. Notice what I did. For international characters, I put in a question mark. That's how I avoided crashing those of you that are on systems where I just didn't know. I thought I had all the answers going into PyCon. Turns out I do not have all of the answers for getting all of you set up to be able to handle international characters. So the question marks represent Norse. Does that look like Norse? Doesn't this look like the credits to Monty Python and the Holy Grail when all of the moose stuff starts coming up? Anyway, and so what we're going to do is we're going to start with this simpler data frame, go to the more complex one, and I'm going to try to take about 10 minutes on this first notebook before our break, and then we'll try to tackle parts of the other 5 in our second hour. How do you know the size of a data frame? How many movies are listed in this title's data frame? It turns out there are a few different ways. The first thing I tried was I noticed that there was something called .size. Oh, that sounds great, I thought. This will give me the size of the data frame. And it gave me this number, and I thought, aha, I have loaded up 430,000 movies. I was wrong, because data frames have both rows and columns. Size is the number of cells, which in this case, because there's 2 columns, is going to be twice the number of rows. So I always avoid using size, and I do 2 things. One, and this is just like a NumPy array that I showed you in that sample notebook, all Pandas data frames have a dot shape. It is anyone know the name of the Python data structure that has parens around it? It's a tuple. Dot shape is a plain old tuple that has the number of rows and the number of columns as the 2 arguments. So I could say something like, titles dot shape and then select out that 0 element if I just wanted to print in front of the user or something the number of movies they loaded. For compatibility with how we're used to using Python, you can also ask for the length of a data frame, and it tells you the number of rows as though it's a list of tuples or a list of lists that you would iterate over. But dot shape and yeah, length, I'll probably use dot shape. I don't like things that after I've typed a bunch of stuff make me go back to the beginning of the line and put like len paren to wrap an expression. So I actually will be using dot shape because that lets me leave alone what I've already typed on the line and simply keep typing in order to get this number out. What are the earliest 2 films listed in the title's data frame? If we're interested in the earliest or the first of something or the last of something, what do we normally do? Yeah, normally in a programming language you would sort. And so here is the head again. The movies just came out of the IMDb in kind of a random order. All you have to do if you want to sort is say dot sort. Guess what argument you have to give that method? Say that louder. Yeah, you have to give it the name of the column because it doesn't know it doesn't know whether I'm trying to sort by title in order to see which ones come first, or whether I'm trying to do it by year. And in this case, this is supposed to be the earliest 2 films. How am I going to narrow this to 2 films? Remember, dot head and dot tail can take an argument if you don't like their default value of 5. So what I'm going to do here is I'm going to say that's a little much. How about you just give me the top 2? And by the way, I'm going to hit, when we're all done today, I'm going to hit save and have for you exactly what I typed in front of you here today so that you can have exactly the solutions I wrote up to play with later. So if it helps you to type this in right now, to try it out, to write it on a piece of paper, do so if that's a good help for you. But I will be putting them up later so you don't have to. Now we get to the really interesting question. How do I select rows that I'm interested in from an IPython notebook? The answer is absolutely crazy. In most of these examples, I'm going to create a little abbreviation for these frames I'm working with so you don't have to see me type the word titles. And actually, I read my code more easily if I have single word names here. This is what first got me interested in NumPy and Pandas. I couldn't believe this was Python code. That is how you get all of the rows that have the title Hamlet. Does that even look like Python to you? Is that like not the craziest thing you have ever seen? And I thought, when I first saw this, I thought, that's kind of crazy. Like, it really looked to me like they were abusing Python syntax. Yes, I know that equals equals can return any kind of object, because if you define a Python object, you can define equals equals to mean anything you want. So obviously equals equals is here returning something that means does the title equals Hamlet, and if you give that to the square brackets that lets you select a subset of it is obviously doing the right thing. But it looked to me like they had cheated when they invented NumPy and Pandas, because what kind of weird special object is that? Well, I got a surprise. If I, let me turn on Pylab, and yeah, it's a little unhappy with me, but it'll, turning on Pylab redefined what cast meant, so let me get that reloading. Remember when I had this little range of numbers from -5 to 5, going 1.0. Whoops, sorry, it jumped around because that load operation that I just did finished. That is one of the things I don't like about the IPython notebook. When you run a cell, it immediately erases its output and then puts it back when it completes, which like tends to scroll you up and down in your browser. I'm sorry, this is obviously something I should open as a GitHub issue and not just complain about here on tape. But yeah, I wish that it kept the old output there, maybe just grayed out, and then replaced it in a single step. What just happened when I reran that load statement up here is this entire page of data just disappeared and was replaced with nothing while it worked, and then suddenly was reinserted, which jumps you up and down in your browser because it doesn't understand why the page is changing size. If I get this range of numbers, I showed you that if I say plus 10, we get all of those numbers plus 10. If I say times 100, we get each of those numbers times 100. Equals does exactly the same thing. In the same way that if I say, so let's get this last number 4, I can say 4 times 100, and I expect an integer. If I say 4 equals 100, I expect a Boolean. This just does a natural array operation that gives me Booleans instead of giving me numbers. If I say equals equals 100, then in the same way that multiply did 10 multiplies, the same way that plus did 10 pluses, this just automatically runs through my array, doing 10 comparisons. Let's change it to something that, let's see, I think the middle number there is 0 between -5 and +5. Yeah. Are these numbers equal to 0? Well, it has to give 10 answers because there's 10 numbers. False, 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 true. False, 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 false. What Pandas does, it lets you use a list of trues and falses as an index back into the data frame. If you index into a data frame and say, hey, here's a big series of trues and falses, it gives you back the rows for which you gave it true. And so this really, really shocked me. When I saw this utter craziness, I thought, oh, what have they done? They've broken Python. That's not something you can do in Python. And it didn't make sense until I realized, oh, this is just like those other operations on vectors. If you have a vector of 200,000 things and say equals equals Hamlet, you get 200,000 answers. And they made this square bracket operator that we always use for looking things up in lists or tuples or dictionaries. They, for a Pandas data frame, defined it so that if you give it a bunch of trues and falses, it hands you back the rows for which true is the corresponding value. And so, using a crazily compact syntax, I'm able to very quickly ask for all of the rows in this data frame where the title is equal to Hamlet. Now let me go back to the schedule. It is just about the time when I said I would take a quick break. And so just to show you the power of this, I'll be doing a lot of cutting and pasting here. Let's just solve one or two more. How many movies are titled North by Northwest? Well, you just do that. And how again do I figure out how many rows there are if I don't want to see them but know the number? I could do len, but my favorite thing is, just like you said, to do dot shape. And then how do I select the number of rows rather than the number of columns? Yeah, take that very first one. So this is how many movies are titled North by Northwest. And we can also combine this magical filtering ability with the operations that I was doing before. We already saw that this is how I could get a new data frame spun up and returned to me that gives me all of the Hamlets. What was the first movie? When was the first movie titled Hamlet made? Well, that's a good question. What did I do before when I wanted to bring earlier movies in history up to the top of my data frame? And what did I dot sort on? Okay, because it'll do it by something else by default. So if I say sort by year, 1910 comes to the top. What if I only want the top row and not all of them? Head 1. I think head 0 literally, let's try. Oh, head 0 just ignores it and gives me all of them. 0, I guess, is a throwaway value for all of them. So head 1, and then if I want, I can actually just say, if I want the right-hand side, I can say dot year. There it is, 1910. But I'll leave it like this so it looks more like a data frame. So you can see how we can get these simple pieces. I showed you first how to sort by year. I then separately showed you how to use filtering to create smaller and more limited data frames from the huge data set we're starting with. And you can here just begin to see how we can chain these simple operations together to start cutting in small steps a big data frame down to size. Limit it so that we get a smaller data frame of only data we are interested in, and then change the data around. An interesting thing that I'll note here is that I believe, and actually let me try this way, I believe we will get exactly the same answer. If I do this, if I move sort over to here, what if I got all 200,000 movies, sorted them by year, then filtered out from that larger set the ones called Hamlet and took the first one, then, we'll ignore that warning for the moment, I get the same answer, Hamlet 1910. Can anyone guess why I prefer, besides the fact that I don't get a weird error, why I prefer this one? More efficient. With that second one, how many movies did I put in order? All 200,000 when I cared about like the 20 that had the name Hamlet. So one thing you'll learn as you work with Pandas is to get expensive things like sorting that has to look at every single row and running that after you've kicked out the rows you're not interested in. All right, right now it's 11:35. Given the delay of about 10 minutes that he predicted in the schedule, maybe this is the moment when people are moving between talks. So let's just break for 5 minutes. I'll be back at 11:40, and we'll finish up the second half. Yes, so it's time for me to get back up and for us to see how much farther through the material we can get. Again, I'm abbreviating things slightly in the interest of time, but wanted to introduce this. Do you think there are fewer than 30 people in the room right now? Because let's see, let me just quickly bring up a window. You think there's 40? I didn't clear the room out enough. I guess I should have said at the beginning that this does presume that you already kind of know Python in order to get going. So now that we are down at least closer to 30, I will reveal to you that if the room had stayed full, I wouldn't even have attempted this. But I received a message before I got up here from Packet Publishing. And I'll erase this before I hit save and then save it for you later. But I was sent the message, we have decided to give, and this is PyOhio, a discount code which is valid on mastering Pandas and Python Essentials. I think it's just a PDF. They don't really send you the book or anything useful like that. But only 30 people can use the code, and then it goes dead. So I want to just put it on the screen. No one tweet this, but since there are a little more than 30 people here, I feel a little bad because you won't all be able to snag this, but a bunch of you are probably thinking, Packet Publishing? I don't want a book from Packet Publishing. And so as long as you guys just don't use it, the rest of the people will be able to pull it up. So I was given that code before it started, and it's only 30 seats, but we might as well burn them up. So grab the book if this Pandas stuff is interesting you. I presume by this point you're in the room because it is. And so I will now get going. So all of the rest of the exercises that you'll do when you pull up exercises notebook 1 later are pretty much variations on what we've just seen. List all of the Treasure Island movies from earliest to most recent. And most of what I want you to take away here that you don't get from reading examples online is the way I iterate to get to a solution. The way that I often start by just kind of staring at the data frame and looking at how it's made. By then saying, all right, let's narrow it down to the Treasure Islands. Notice this is close, but not quite what I want. They're not in order yet. So finally, a sort by year, that's the process that you'll learn. That's one of the main values of having me in front of you for an hour or two is getting to see the intermediate moments where it's not the solution yet, when we're just at this point and we're pulling the right data, but it's not in the right order, or where we haven't tallied it correctly. So really pay attention here to the process by which I try to take small steps, because it is hard until you get good at this, to just read a question and write out an answer. It is easier to take one little step at a time, sometimes backing up if you get the wrong thing, until you've narrowed something down to here. The first Treasure Island movie was in 1918, and then the most recent was in 99. Was that the Muppets one? Okay. And had Muppets in the title? Okay. So it would not be confused with the other 7 movies in movie history named Treasure Island. How many movies were made? I'm going to cut and paste to make this faster. How many movies were made in the year 1950? Guess what I'm going to change. Instead of checking whether .title equals Treasure Island, I'm going to say whether .year equals, now that's an integer field, so I'm not looking for whether it equals the string 1950. I'm going to look for whether it is the integer 1950. And first, before I do anything else, I'm just going to let it display it. Take a look. Be high touch with your data. When you make a recipe from Julia Child's The Art of French Cooking, it constantly is saying season to taste. And if you're not used to that, you feel guilty. Because like you go to all this work and this much French food comes out for 4 people, and you don't want to waste any of it. But seriously, if you're not constantly tasting, you're just going to be guessing with how much salt and pepper you throw in. And with your data, be high touch. Don't try to take 3 or 4 steps. Take one little step and look. Did I really select the 1950 movies, or did I just type something that I thought would select the 1950 movies and accomplish something different? This looks like I've really selected a lot of 1950 movies, so I'm now going to ask for the shape. This is 1,000 rows and 2 columns, and I will ask for element 0 there in order to just get how many movies were made in the year 1950. Hollywood made about 1,000 movies. 1960, they were up 50%. They made about 1,500. All right, now this is a tricky one. How many movies were made from 1950 to 1959? Now, because that the official thing I'm going to teach you here is that you might think that you could do this. You might think, well, all right, I want all of the movies where the year is greater than or equal to 1950, and where t dot year is less than or equal to 1959. This is what you would normally write in Python if t were a scalar value, that is not an array, but just 1955 or an integer. If t dot year were just an integer, this would work just fine. In Pandas, however, you get a value error. The truth value, and it makes no sense. Like, I can't, like that error message doesn't tell me what I did wrong. I have no idea. So what's happening here is, I told you that Python objects get to override what plus means, what minus means, what multiply means, what greater than, what less than means when run on that type. And so the NumPy people and then a Pandas person were able to go in and say, haha, well, for my type, it means 10,000 less thans. You don't get to do that with these words and or. They are such fundamental concepts that they don't ask the type. They simply want the type to be either the value true or false so that they can and or them together. And so and is turning first to the left, asking this value, okay, are you true or are you false? And is getting a value error. Well, you know, the truth value of a whole series of trues and falses is ambiguous. You can ask me if I'm empty, if by and you mean, you know, is there anything inside of me? You can call .bool, you can ask for a particular item, you can ask whether any of my items are true, or demand that all of them be true. But you can't just ask me if I'm true or false if I'm 1,000 true and falses. And so they had to do a hack here. They couldn't override and or, but they could override the and or that sets use to combine either the things in both of a pair of sets or in either of a pair of sets. That's the and the or character from the C language, the bitwise and or. Only problem is that if you try to use it, you get another value error with exactly the same problem because it turns out that and, because it was meant for just combining bit fields, it's like the multiply sign, whoops, I hit the down arrow. It binds more tightly than does these operators. So when I type this, Python reaches in its back pocket and brings up its order of operations and says, ah, ampersand binds more tightly. And so it first tries to say 1950 and t dot year and runs into the same problem with that logic. And so this is one place where you have to force the order of operations. I'm not used to having to do this in Python, unless I'm adding 2 numbers that I'm then multiplying by a single coefficient. But this is one place where you'll see a lot of parenthesis in Pandas code. I have to force the order of operations and say, no, 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 no. Do the t dot year comparison and give me trues and falses. Do the other t dot year comparison and give me trues and falses. And then let us and those lists together, producing a hybrid list of trues and falses that only has true where both of the original lists, left and right, had true. And so This is a trick that you learn that let the Python peoples get around the fact that the keywords and or couldn't be customized in order to be vector operations in Python. Now, there is another thing that we can do. If we get t.year, notice it displays a little more uglily. If we display a data frame, it's all pretty. It tells us the titles up at the top, and it has the indexes down the left-hand side, which here aren't very interesting because they're just the row of the CSV file that it read in. By the way, I've been throwing that around, and it only occurred to me during the break. I hadn't explained what a CSV file is. If I look at data, titles.csv, CSV means comma-separated value. It's just a plain old text file that has commas between the title of the movie and the year. By convention, usually the very first line is an exceptional line. It's not full of data, it's full of titles for the data. So the first row of the CSV that you save from Excel is typically the names of your columns, and then all of the subsequent ones are the data itself. And again, if you study that operation I did up at the top from CSV, you'll learn all the options you have when reading in a file like this. So when you look at a data frame, it's pretty, you have different columns, everything's labeled. What are each of those columns? Each of those columns is what Pandas calls a series. If you simply look at .year, it's simply a series of integers, 1984, 1946, and so on. If you look at t.title, you'll simply see a plain old series of strings. And I am less happy with how series print out because instead of using pretty HTML that I can style and add colors to, it reverts to this plain text rendition that just has the index on the left. Again, here it's just auto-indexing the lines of the file starting from 0. And on the right is the data value itself. I always find it a little disconcerting when I'm in pretty HTML formatted land. I innocently pull out a series that I want to look at, and suddenly I'm back in the 1980s with plain text. I suppose rather than complaining about that publicly in front of a camera, I should just open an issue. I'll think about that. Yes, sir. Well, let's look. My browser didn't crash. ... So it was indeed. Good question. Series are as intelligent as data frames are in how they display. They're careful not to fill your screen with more data than you necessarily want to look at. So t.year is very much like a NumPy array that I was playing with earlier. It's just a sequence of integers that has all these operations. I can multiply all the years times 1,000. I can subtract 1,000 from them. They're just, it's called broadcasting if you ever run into that term in documentation. Pandas, NumPy, they do automatic broadcasting. You ask for one operation, you get 10,000 or however many rows of data you have. In order to know what years are in a decade, you can cheat. If you divide by 10, then you get this fraction hanging off the end, but Python does have a truncating division operator that throws fractions away. It only keeps the whole number part. And so this is really the decade of each film. 198 meaning the 1980s, 194 meaning the 1940s. Again, take it away, you see the full year. Truncate divide by 10, and you get only the first 3 digits. If we multiply then by 10 to put the 0 back, we have a quick way to get the decade of a film. If you think decades start with the 0 year and end with the 9, which is what I do because it makes the math easier. If you don't think that, if you know that we actually began with the year 1 because we didn't have 0 technology in our math at that point, you can, I believe, subtract 1 from the year and get the other kind of decade out. But I think Hollywood often considers the 1980s to be all of the 198 years. So this matches the data set. So the question is how many movies were made. Now this is something interesting. You previously have seen me only doing math, only doing comparisons with columns, with series that are actually in the data frame. T.year is this thing that lives in the data frame, and I've been comparing it to 1950. Watch this. This value, T.year divided by 10 times 10, isn't in the data frame. You know, just because I compute it here doesn't mean that it has suddenly appeared in the data frame. This is a throwaway intermediate value that I've created, and yet I can do the same kinds of comparisons on it that I did on series that lived in the data frame. I've created a temporary series with decades in it that lives outside of the data frame, and it follows all of the same rules as the series that are inside the data frame. It just happens to live outside of it as an object. And so I can simply say equals 1950 in order to get true values here wherever a movie was in the 1950s. And so I could get my T data frame, my titles data frame, and I could sort it that way. Oh, never mind. The question wasn't to list all the movies. It was to show how many. And so this is another way, without having to use parens and that little and operator. This is another way to use parens. Oh, except that I don't need them. It knows that math happens before equal signs. So I now am getting all of the 1950s movies. In what year has a Batman movie titled Batman been released? Let's see, I'll go ahead and do that because that's quick. Now again, I always just start by looking and to remind myself what this data frame looks like. I want all of the rows where T.title is Batman, and I get them, and then I just want the years. So I'm pulling out, again, the indexes. This just means the 45,000th line in the file, the 81,000th line in the file. Here are 2 years, 1989 and 43, that were the 2 years in which a movie simply called Batman were ever produced. And then I'll finish this series up by showing how many, by looking at this cast data frame that we haven't looked at yet. It has a lot more information in it, so for a moment I'm going to go to a smaller font size, just so for a minute it fits here. It has title and year, so each movie can appear 10, 20, 30 times in here, once for every person who has a name plays a character. So how many roles were there in the movie Inception? Well, I simply say, let's grab all of the items here where the movie title equals Inception. And note, I know that I could put .shape and immediately get a number out, but I want to see the data. I want some hint of whether I'm doing the right thing. So let's see if any of the characters in the movie Inception come up. So I recognize Michael Caine. I recognize Leonardo DiCaprio. See, that's what I love about this IMDb data set. I have some hint of whether I've done the correct filtering here, because I kind of have an idea of who is in the movie Inception. Now that I have an idea, I can come up here, I can ask for the shape, and then say, well, I don't care how many columns there are. Cast has 6 columns. I just care how many rows there are. How many rows, and we'll learn 2 last kinds of filtering here, how many roles in the movie Inception don't have an in value? What's an in value? Well, let's look at the data frame. Oh, okay, have you ever seen, like on a Hollywood poster, like someone gets to go first, and someone gets to go second, and someone gets to go third? That is represented in the IMDb by a number in. You'll remember the scene in Shakespeare in Love where the actor comes in and says, who was the playwright that was killed, Shakespeare's big rival, and he dies in, the actor comes in and announces, and everyone's suddenly sad, this famous actor's been killed, and they said, how? He said, and this is historical, he was just killed in a bar in because he got in a fight over the bill. And the lead actor just says, oh, the vanity, the vanity. Another guy says, no, not the billing, the bill. Thinking that the actor had died in a fight over who gets to be number 1 on the movie poster. So that's called the billing, but I just called it the number in to make it easy to type. And you can see that some people are so low ranking in Hollywood that they don't get a specific in value. There was a definite negotiation made as the contracts were signed that Leonardo DiCaprio is number 1 and that Joseph Gordon-Levitt is number 2. Like that was, you know, that's something you get in writing, and that is a very, very important thing. But the LAX passenger and the Mombassan gambler, in their contracts, they don't even get to specify. They are down, in IMDb, I think you have to click through to full cast even to see them. In many science data sets, we have missing data. Days on which the weather station was down, so you just don't have a temperature. Nights on which the satellite couldn't be contacted. Temperature ranges for which your sensor isn't rated. You're often winding up days when one stock that you follow is being traded, but the international stock in the other company might not, their stock, it might be closed for a holiday in that country. You very, very often in financial and science data sets wind up with holes in your data. Pandas represents those as the IEEE standard value, not a number. It's a value that can fit in the same slot in your computer's RAM as a real number, a number with a value, but it signals your math coprocessor that it is not a value. If you try doing math with it, yet another not a number comes out, because not a number times 3, you still don't know its value. And we can't easily use an equal sign to pull these out, because they're not equal to each other. Two things you don't know aren't necessarily equal, right? And so we can't use this trick of the double equals sign. Let me, by the way, I'm going to use a trick I often use. Here, C is briefly a name for this entire cast data frame. I'm then going to throw that out, and on this line of code, I'm going to reuse the name C for this more limited data frame right here of everyone in the movie Inception. That lets me go and run several lines. That way I don't have to do all my computation on a single line. I can do smaller steps. I can comment them out if I decide some of the steps might have been mistakes. And what I'm going to do here is I'm going to do a second filter to show you if you want to know the roles that are not ranked, you say C.in, the column n, and you can't use equals, you have to say is. You would think it would be is NaN. Maybe I'll open an issue. But because NaN is, because databases people call this, SQL people call this the value null, in order to match the behavior of other data libraries, this is actually called is null. And you can see here that by using that to select out rows, we have gotten rid of Leonardo DiCaprio and Jason Gordon-Levitt, and are looking here at only the people that in their contract didn't even rank a specific ranking in the list of actors. If you want to ask the opposite, guess it is not called is null, it is called not null. I use that a lot more often because not null can let you pull out the lines of data that do have meaning. Here we are getting the full cast that had in their contract some kind of value. And as a final step, we can decide to display the cast of north by northwest, not in whatever crazy order they come in from the Internet Movie Database, but in their correct in value. How will I do that? How will I get them in order? Dot sort, and then in the parens I will put the name of the column that I want sorted by. And so here we have the names listed in the same order you will see if you go look at the movie poster. Did I see someone had a question?
Can you use other Python conditionals like in or starts with or anything like that?
Yes, if you look at, and let me go ahead while that question's on the table. Can I get to the, what's it called? It would be called the Pandas API documentation. Oh, good grief. I'll bring that up at the end because the way I've maximized my window isn't letting me do Google searches very easily. But in the documentation, there's a whole stack of string operations that you can learn. And I'll show those right at the end. And so given those operations, you could go through fairly easily, I think, the rest of these exercises. They'll just have you do those same basic operations: filtering, sorting, and then either taking the number of rows or showing the head or the tail to answer all of these questions about movies, actors, actresses, and how many times they've appeared in different films. I, for the moment, in the interest of time, will now have only a few minutes each to give you a brief introduction to the other notebooks and show you what they're each about. All right, the second notebook, they all begin with exactly the same 4 lines, so I'll go ahead and run them and get those data frames loaded up. The second one lets you exercise a great superpower of series. Remember, each column is called a series, just a list of values. And series let you do things like, what are the 10 most common movie names of all time? Well, that's probably going to be done by looking at our list of titles, because remember, cast isn't good for questions about movies because a movie can appear once or 100 times, depending on how many people are in the movie. It's the title CSV file that shows each title once. What are the 10 most common movie names? Well, I know I can I can stop thinking about the year and just look at that series of titles by saying t.title. It's wrapping here a bit awkwardly, but what would I do if I wanted to know the most common? And so the second set of exercises here is really designed to get you practice with a superpower of the series called, I always want to type, count values or value count, because I'm a programmer. I'm used to methods that are verbs. This one's a noun. You ask the data frame, make this smaller, so there. I had to make the font smaller on you to make it wrap correctly. The dot value counts of a series runs through the entire series, tallying up how many times it has seen each unique value. And so this has figured out how many times each movie each title appears in the data set, and it goes ahead for you, just as a guess. It doesn't know what order you want them in, and it puts them in order of popularity, with the most popular at the top. What if I just wanted the 10 most common? What would I do to this big data frame? Yeah, head 10. So those are the 10 most common movie names of all time. You can do things, which 3 years of the 1930s? Obviously, what you'll do there is you'll have to use from lesson 1 your filtering to get only 1930s movies. Then pull the years, do a value count, and pull out the 3 winners, the most popular. Plot the number of films that have been released. All right, this is a new thing, so I'll do it out in front of you. Plot the number of films that have been released each decade over the history of cinema. All right, what do we got here? We have some years. And for each year, we want to know how many times it is the year of a film. 1910, how many films have you as a year? All right, so we ask for not the value counts of the title that told us that Hamlet is the most popular remake, but the value counts is now going to tell us which are the most popular years. 2015 is the most popular because we keep, in general, making more and more movies through history. But you'll notice this isn't quite in order. The number of titles already in the IMDb for 2016 puts it between 2008 and 9. Like if no more movies were announced for release in 2016, it would already be like the 6th or 7th biggest year ever for number of movies released. The fact that these years are not strictly in order is going to create absolute havoc if we say .plot. Because .plot simply goes back and forth through your data in the order that the data dictates. And so if your data starts with 2015 and 2014 and then jumps back to 2016, look, you get a jagged edge jumping back over to the other year. Plot, which is the superpower we're learning here, because that's really convenient. Few times in Python can you just say .plot and have a graph come up already loaded with your data set. It's fun once you figure out that you need your x coordinate in order. Unless you want the jagged line, sometimes you do. In this case, we don't. So if this were a data frame, I could just say .sort with a column name. But this is a series. It doesn't have columns. It's just a single series of numbers with an index. And so here we get to something that is fundamental that I haven't had to tackle yet. What is this thing over to the left? You'll note it is not, strictly speaking, a part of our data. It doesn't have a name. If I wanted this 0, 1, 2, 3, 4 from this particular data set, it's not a column. There isn't a name up at the top of the 0, 1, 2, 3, 4. It is something that is not part of my data. It is alongside my data, and it is called the index. And we will see there are operations for getting things that are data and whoosh, making them move over and for a while becoming your index that you can do indexing operations on. Then you can move them back over to being normal columns again. When you do a value counts, you get a single list of numbers, your data, sitting next to a quite different sort of thing, your index. Indexes make it very easy to jump in and grab data because they're an index. They have special data structures behind them to make access very quickly. So we can't use sort here if we want the years in order. We have to use something called sort index. Sort index does for your index what normal sort did for our data. Sort index gets all of your rows and uses that index hanging out to the left of your data to put it in order. And it is by putting the years in order that we're going to get a reasonable plot showing us the number of movies in the IMDb for each year up through, I guess they're already predicting movies out in the 2020s, but only a few are being predicted or planned that far ahead. So far, it's looking like 2015 will be the biggest movie year in history, and then it'll like tank. So this shows that on the one hand, Pandas has this really, really powerful ability just to draw a plot without you even having to name what you want. It understands index is probably your x value, y is probably the data, but because it's just drawing a line from point to point to point, if you wanted an index order, you're responsible for doing that. Plot the number of Hamlet films is the same thing, except that you'll ask for the title to equal Hamlet. And I find it, so first it's given me a completely ridiculous value, so as usual, I'm just going to be high touch with my data. I'm going to kind of look at it like this. Oh, okay, and so I get the dot year. Does that do the right thing? Yeah, looks like the years of those Hamlet's movies. Notice what I'm doing. I'm going back through my work, and whereas in other languages I'd have to add a bunch of print statements and take a bunch of things out, here I'm just able to carefully, one step at a time, iterate on a single cell because I'm in a notebook. Okay, value counts. Okay, oh, made each decade. What surprised me is that the line was straight, and I was expecting it to go up and down. But never has there been more than one Hamlet in a single year. Why? Because the IMDb would have called the second one Hamlet parenthesis 2. You know how they put those Roman numerals to disambiguate? So the question, in fact, was the number of films made each decade. So I don't want the year, because there's only going to be one thing in 20. They're coming out with Hamlet this year? Only one thing in 2015 called Hamlet. Let's divide by 10, multiply by 10. And now we get per decade. How many 1980s? How many 1970s? The number of Hamlets. It looks kind of silly to get numbers like 1 and 2 and 3 and plot them with a line. So I'm going to turn this into a bar plot instead because I think that's a little more reasonable for this data set. So, not since the 1910s, the dawn of silent film, have there been as many Hamlets in a decade as there will be this decade. My friends, we are living in a golden age of cinema. First Fury Road, and now Hamlet. And so again, notice how I've tried to construct these exercises when you go through them later so that they start asking you to pull together and notice the exploration that it requires here. Don't be afraid to explore, to try one thing and then another, because it takes a little while to figure out how to put the pieces together. And so the other exercises here are similar. Plot the number of rustler characters in each decade of the history of film. So here, we don't want titles. We want cast, and I'm just going to move forward from there. So, okay, if we want the rustler character, what column am I going to look at? Okay, so character, C dot character equals, and I'm not going to try to graph it until I've kind of looked and seen, oh, and yep, there are all the rustlers. Anyone want to guess what decade is going to come up as the winner here? 1930s. If you are one of those extras that just looks like a cattle rustler, go back to the 1930s. There will be jobs and more jobs available for you. On the other hand, number of Hamlet characters each decade has only been going up. And you might wonder, how can there be 20 Hamlets in a decade if there's only like 3 movies called Hamlet? And it's because like if there's a play, a high school play in a film, they'll sometimes just name the character Hamlet. Or of course it could be all those Hamlet 2, Hamlet 3, Hamlet 4s that are in the database that weren't caught by my earlier operation. And so we have some other things here. Most common character names. That is just asking you to get c.character. What do we do if we want to run a popularity contest on a series? Yeah, value counts. And we only want the 11 most common, so we'll do this. So the most common character name is himself, appearing as himself. Dancer, extra, reporter, doctor, policeman, student, bartender, nurse, minor role, and party guest. What do you think number 12 is? Yes, number 12 is zombie. So that leads to something interesting. So there are characters named herself. Well, who most often in movie history has appeared as herself? We could say, well, we want the character name herself, and then that would give us all of the herselfs, and we would want to have the actor's name be what we, one step at a time, we'll want that to be what we run the popularity contest on. Who is Joyce Brothers?
The Surgeon General got fired for promoting...
Well, I wonder why she would be in a lot of movies. Anyway, Queen Elizabeth II beats out her own prime minister, Margaret Thatcher. And so you can see all of the most popular herselfs. Okay, only giving you one guess. Who is the most popular himself in movie history? No. He's not just the most popular, he is by far the most popular, like 3 times the number of appearances of his nearest, because, of course, every Indiana Jones movie set in World War II, every movie that has, they have to credit, if they show a piece of archival footage on a TV in the background or a movie reel that a character's watching, they have to credit the president or the figure, and he's a popular one. And so the subsequent questions will get you to go through these different operations and combine them together in different ways. One that I'll show you that uses one little trick is that plot the in values of the roles that Judi Dench, so we want only the rows where the name is Judi Dench, plot the in values of the roles that she has played over her career. You might think that you'll just pull out, let's see, the in values of the roles. All right, we want to plot this over time. We don't just need .year. We don't just need .in. We kind of need the years and the ends together, because I want to plot her career as it's moved from supporting characters to main characters, I mean, whichever direction it's gone. And so if you need plot to ignore your index, because that's just the row, remember, in the file that you read in, if you want it to use an X and Y of your own choosing from this data set, then you can ask for X to be, let's say, the year. That makes sense. And the Y value to be the in. And I don't need a line. I don't need lines drawn back and forth. Let's just do, I believe it's called a scatter plot, where you just put a dot. And since none of her values are negative, I don't really need it to go all the way to -10. Let's say that X limits are 0 through whatever it wants to choose. I'm sorry. That goes back. This is her career all the way back to the year 0. I always get this backwards in front of audiences. I mean, Y limit should go down only to 0. So we see here that she began, I believe she began on the stage and in British television and only was doing occasional movies. We can see the number of movies per year has really picked up into the 1990s and the 2000s. And we can see that the variety of roles has really expanded over time. She's gone from playing bit parts, whose in value is down in the 30s and 40s, up to quite a number of leading roles, but also secondary roles. And we can compare that data to the in values of Cary Grant, which is he was a little more snooty about the roles that he was willing to play. So this is a fun thing. Sidney Poitier, the Academy Award winner, had an interesting career. You can see in values putting him 3rd and 4th in the billing, then began to move up into a mix of leading and supporting roles. Then, in the 1970s, was just kind of on fire, all leading roles, and then late in his career was willing to take 2nd or 3rd billing, or was included in archival footage that was not billed very high. How many leading roles were available to actors and how many to actresses in the 1950s? And here I was just, this question is just asking you to state those 2 numbers. As we're getting low on time, because I've gone into a good deal of detail here, I'm going to jump right ahead to the exercises 3 and answer a more interesting question in order to show you a final superpower called group by. And I'm going to, rather than doing, oh, come on. My computer's pausing because I have so many of these things open. That is, I have, many copies of this data set now in RAM. So let me shut down those 2 files so that only exercises 3 is running. how many leading roles were available to actors and actresses in 1950s, the 1950s decades as a whole. These will all be list in order. So how many roles were available to actors and actresses for each n number? We're going to do this by grabbing our cast, which I always call C when I remember to define it. And all right, here we have a bunch of roles from all years. So we're going to ask for year divided by 10 times 10 equals 1950 and not get anything out. Why did nothing display? I forgot to ask for it to be printed once I had built it. So let me put that little bare expression that will get it actually displayed. So here we have a bunch of type actor roles and type actress roles, all of which are from some year in the 1950s. By the way, this is a binary distinction which very often doesn't exist in real life. If you're ever setting up a real data set, there are good guides online about, for a number of reasons, it's best not to have a binary type when you're trying to identify someone's gender. Hollywood doesn't know this. The Academy Awards are for actor and actress with no other alternatives. So this is a data set that actually does force everybody playing a role to choose which of those two labels they will take on because that's necessary for things like the Oscars. So this data set is doing something that you normally can't in real life, but Hollywood, it's not real life. And this is one of the ways. Decade as a whole, how many roles? So I want the n numbers 1 through 5. So what I want is I want C dot n to be greater than or equal to 1, and C dot, this is just from the, I think, first page of exercises we did. I want only 1s through 5s. And now, how many total roles are available to actors and actresses? There is this magic ability in Pandas. One, you can say, get this whole data set and group by year. And then we'll just take the in column out of that. Oh, I'm sorry, you have to ask. Once you group by, it doesn't know, well, do you want the average of each group? Do you want the maximum or minimum value in each group? Do you want the mean, right? Because when I have a group of numbers, there's a lot of different ways of putting them together. So what you do here is I just want the size of each group. I just want how many fall into each group. So here, for example, are the number of roles per year. Over the 1950s, it generally trended upwards. Here is the number of leading roles, supporting roles, and slot 3, 4, and 5 roles for the whole 1950s. Finally, if I say, I believe it was called type, I can find that if you were in Hollywood looking for a job, there were over the 50s 27,000 actor jobs open, but only 15,000 slots for actress jobs. The real magic of group by is that you can give it several things to group by. So you could say group first by type and then by n value. And it does all of the work of grouping however deep you want to go on having main categories and subcategories all the way down. Now, this is interesting. I want to kind of look at how was the distribution of actor and actress roles differently for n equals 1 and 2 and 3. And here it's kind of hard. Like if I want to compare the 1, I have to move my eyes from up at the top to down to the bottom and back up. And so I'm actually going to switch this around. If I simply name them in the opposite order, it will be the n value at the left and then the type that comes next. And notice how this is brought right next to each other. The n equals 1 values. This is interesting. Notice that for whatever reason, supporting roles are fairly evenly distributed in the 1950s. If you are one of those n equal 2 kind of actors or actresses, you're not Cary Grant, but you're next to Cary Grant. The number, for whatever reason, there is almost gender parity if you want slot n equals 2. If you want 1 or 3, for whatever reason, sociological, and so forth, there are very, very great disparities in all of the slots except for 2. Let me show you a last maneuver. Wouldn't it be neat to be able to do some math, which exercises 4 asks you to start doing math to do this as a fraction? Wouldn't it be interesting to see a graph showing you a comparison? And the problem is, as you've seen with all these math operations, they just go down comparing things. It's not easy to get subtraction or division in Pandas and NumPy to compare up and to do operations up and down. Plus and minus don't want to look up and down between rows. They just want to look at a single row. When I've plotted, when I've done math, it's always been in a single row. So Pandas gives you a way to pull data up so that it shares roles. There is something called, if I have the name right, unstack. For example, I can ask for what a moment ago was index data, 0, 1, 2, 3, 4, 5. I'm sorry, 1, 2, 3, 4, 5, to become columns. So now I could name them. On the other hand, I could unstack the type, and I've now put next to each other those pieces of data that I wanted to compare. And so if I have this data frame, all I need to do, if I want to know the ratio, let's say the percentage of all roles at that in value that are actor roles, I can say number of actor roles over the total. I have to use parens because, of course, the way that grouping works. And now I have a number, a fraction that I could graph over time. And I'll do this as my last operation because it kind of brings together almost everything taught here in the tutorial. I am going to, for every year of cinema, try to figure out, let's say for the first 3 in values, how the distribution of those in values was related to the gender, binary in the case of Hollywood, of the actor, which again, not something to do in real data sets. So I'm going to get the cast. I'm going to ask for only cast positions 1, 2, and 3. Okay, it looks like that worked. I'm then going to group by both in and type, take the size of each of those groups, and then unstack by type. For a second, I'm like, wow, this is taking a long time. Why did nothing print out? Because I didn't tell it to. Let me get the, yeah. Oh, I didn't get out what I wanted because, of course, okay, I actually, if I want to do this, I've lost data here. I only ask for 2 things, but if I'm going to do this over the history of film, I also want the year. So here we have it. For every year of film, under year, we have how many leading roles there were. And it'll look more natural to me if I actually do this in the opposite order just for fun. Well, I can switch it around later. All that's important here is that I have the information because I'm going to now take this ratio. Notice that when I try to do operations on not a number, it just shrugs and gives me not a number back because that's where I lack data. So if I divide 2 numbers, one of which I don't know, I still don't know the answer, and it's very scrupulous with that, which data scientists love about Pandas. So now that I have done that, I still have all of these values for n equals 1, down then in the omission here, the n equals 2 values, finally the n equals 3. So watch this. I will, as my finale, do a final unstack. So first, I just had 3 things, in, type, and year. I unstacked type to get actor and actress on top and combined those values by year. Now I'm going to unstack on n. So instead of plotting a single line, I'm going to plot 3 of them over movie history. An n equals 1, an n equals 2, and an n equals 3 line. Go ahead and sort by year, just for, sort index, because year is my index. And then I'm going to do a plot. And we see that. And let's go ahead to and make it go from 0 to 1. just so we get some scale here. There are so few people in films back in the 19-teens that those numbers, as you can see, have a wide variance from year to year. But as Hollywood really gets going, again, this interesting pattern that we saw in miniature in the 1950s is that the leading role, n equals 1, about 75% of the time is an actor role. That kind of ramped up to 75%, and only in the 2000s, the 90s and 2000s, did it bump back down. The red line, which is the n equals 3, the supporting character, back in the 30s and 40s, was very likely to be an actor, but has slowly been trending downwards to more often being closer to parody. And then for whatever reason over the history of film, it has been that n equals 2 slot that is at times, in some years, almost a coin toss between whether an actor or an actress will be playing the supporting role. So this is a very simple data set. It's just a list of everyone who's been in an IMDb film over time. But using Pandas, using 3 or 4 lines of fairly compact code, we can pull out some interesting sociological observations about the history of film. If you'll go through these exercises later, there'll be many more examples that will give you practice, but these are the essential maneuvers. If you practice them, make mistakes, correct the mistakes, and get used to them, there will be lots and lots of questions you'll be able to answer, not only about Hollywood, but about your own data as well. Let me briefly here get control of my browser. There, now I can do web searches. I promised to show you 2 things. First, if you look up Anaconda, when I was teaching this last year, the Python product was always the first thing to come up. It no longer is. There's another problem, by the way, which is that if you simply go to the Anaconda page and click on download, it asks you for your email address. Like, how intrusive is that? Look up instead Anaconda download, continuum.io downloads, and you go right to the page that otherwise they want your email for you to visit. Anaconda is not just good for the IPython notebook. Look at all of the Python packages they already have up and running on Windows, on Mac, and on Linux. Not just data libraries, not just science libraries, but things like gEvent, Django, Flask, and things SQL Alchemy, Paste, Pillow for image editing. All of those things, they've already gotten the third-party libraries, gotten the C libraries, gotten it all compiled, and gotten it ready. So Anaconda is a great way to get started on Python if you don't like spending all day installing things. The other thing I promised to show you was the Pandas. I usually, once I got my feet under me with Pandas, I love just going right to the API reference. It lets you just category by category see every single thing Pandas can do. The 2 things I really didn't have time to cover were the fact that if you have a series that is some dates and you want to reach inside and learn the year or the month or the day, you can, there's a little namespace. They didn't want the names out interfering with all their other method names, so they hid inside of a little .dt for date time namespace all of these attributes that you can access to get at the pieces of a date if you want to graph dates by their month or by their year. And there are exercises that will get you to do that. You'll find out what month do Tom Cruise movies tend to come out versus what month do Judi Dench movies. It's a very, very different distribution over the year. And the other thing is someone asked about string operations. Go through this section on string handling. Any series, like movie titles, like character names, like actor names that you pull out, you can say the name of the column, .str, S-T-R, dot, and you'll have all of the normal Python operations and more for doing string operations, starts with, ends with, and things that can let you handle those as strings. Thank you very much for your time, and I hope that gets you started.